3 points make a circle. Take any 3 points in the plane that don't sit on a single line. There is exactly one circle that passes through all 3 of them, always. Pick 3 more, different ones, totally unrelated, and you get a different unique circle. This is the deepest fact in plane geometry that nobody bothers to mention. 3 is the magic number. 3 points define a circle. Now ask the next question. What about 4 points? Almost never. 5 points? Even less likely. 6? Astronomically rare. By the time you reach a handful of points scattered randomly in the plane, the chance that they happen to share one circle is essentially 0. So here is what we are about to do. We are going to start with one triangle. Any triangle, doesn't matter what shape. From this triangle, using rules that have nothing to do with circles, we will construct 9 specific points. 3 from one rule, 3 from a different rule, 3 from a third rule. The 3 rules will share nothing in common except the original triangle. And then we will draw a circle, and every one of those 9 points will be on it. This is the 9-point circle. It was discovered in 1822, and after 200 years it is still considered one of the most surprising facts in elementary geometry. Start with a triangle. 3 vertices, 3 edges. The first 3 points are easy. Take each side of the triangle, find its midpoint, the exact center of each edge, 3 sides, 3 midpoints. Mark them. This is the medial triangle. If you connect the 3 midpoints to each other, you get a smaller triangle sitting inside the original. Each side of it is exactly half the length of the corresponding side of the parent, and the whole shape is rotated 180 degrees around the centroid, so it points the opposite direction. The medial triangle of an upward pointing triangle points downward. These 3 points feel natural. They are the most obvious special points on a triangle. They have nothing to do with circles. They are just the centers of the 3 sides. So far this is grade school geometry. 3 midpoints, no mystery. Now hold these 3 points in your mind, and watch what happens when we add 3 more from a completely different construction. The second rule. From each vertex of the triangle, drop a perpendicular line to the opposite side. The line that hits the opposite edge at exactly 90 degrees. This is called the altitude. 3 vertices, 3 altitudes. Mark the 3 points where each altitude meets the side it lands on. The feet of the altitudes. These 3 points have nothing to do with the midpoints. The altitude from a vertex lands wherever the geometry forces it to. For a thin, sharp triangle, the foot might be near a corner. For a wide, flat one, it might be near the middle. For an obtuse triangle, the altitude can even land outside the side, on its extension. 3 altitudes have a famous property of their own. They all pass through one point. That common intersection is called the orthocenter, the place where the 3 perpendiculars meet. We will need it in a moment. For now, focus on the 3 feet. The midpoints came from cutting each side in half. The altitude feet came from dropping perpendiculars. Different rule, different points, 6 points so far. You should not expect any of them to be related to each other. The third rule needs the orthocenter, the meeting point we just found. Once we have it, the rule is straightforward. Take each vertex of the triangle. Draw the segment from that vertex to the orthocenter. Find the midpoint of that segment, the exact center halfway between vertex and orthocenter. Do this for each vertex. You get 3 more midpoints scattered around the figure. Mark them. We now have 9 points on the page. The first batch came from cutting the sides in half. The second came from dropping perpendiculars onto opposite edges. The last came from bisecting segments to the orthocenter. 3 rules, none of them obviously related to each other. 9 points scattered across and inside the triangle, in a generic configuration of 9 random points. The chance they all sit on a single circle is so small you can ignore it. The space of 9-point arrangements is enormous, and the slice of it where the points happen to be co-circular is microscopic in comparison. And yet, watch this. Through the 9 points, draw a circle. Just one. The circle that passes through any 3 of them, say the 3 midpoints. Now look at the other 6. Every single one of them lies on that circle. Let it sink in for a second. The 3 midpoints, the 3 altitude feet, the 3 midpoints between vertices and the orthocenter. They are all sitting on a single circle, and the circle does not move when you change the triangle. Stretch the triangle, squash it, rotate it, make it obtuse, acute, almost degenerate. As long as it is a real triangle, you get 9 special points, and they all sit on one circle. Always, forever. This circle has a name. It is called the 9-point circle, sometimes the Euler circle, sometimes the Feuerbach circle. The center has a name too, the 9-point center. The radius is exactly half the radius of the original triangle's circumscribed circle. We will see why. The first time you watch this happen, the natural reaction is that something is wrong. There is no obvious reason for 9 specific points, defined 3 different ways, to conspire onto one circle. But they do, and the proof, when you see it, is one of the prettiest things in classical geometry. The result is usually misattributed. People call this Euler's circle, but Euler did not prove it. The first complete proof was published in 1822 by a young German schoolteacher named Karl Wilhelm Feuerbach in a 40-page pamphlet titled Properties of Some Remarkable Points of the Rectilinear Triangle. He was 22 years old. He never held a research position. He taught at a gymnasium, the German term for a college preparatory secondary school in Erlangen, and he wrote his pamphlet while teaching geometry to teenagers. Feuerbach also discovered something even more astonishing about this circle, which we will get to at the end. He died at 33, in poor health, in obscurity. The pamphlet sold poorly during his lifetime. Henri Turcom, a French mathematician, named it the Cercle des 9 points, the circle of the 9 points, in 1841, 2 decades after Feuerbach found it. Slightly earlier, in 1820, the French geometers Charles Briançon and Jean-Victor Poncelet had proven a related result. They had shown that 6 of the points are co-circular, the midpoints and the altitude feet. They missed the third trio. Feuerbach saw the full picture. 2 centuries later, the result still appears in every advanced geometry textbook on Earth. It is the keystone of triangle geometry. So how does the proof actually work? The first half of the proof is the easier half. We need to show that the 3 midpoints and the 3 altitude feet, 6 points so far, all sit on one circle. Start with the 3 midpoints. They define the medial triangle, which is similar to the original, scaled by exactly 1/2. This medial triangle has its own circumscribed circle, the circle through its 3 vertices. 3 points always define a circle, remember? So the 3 midpoints define a unique circle automatically. Call this our candidate circle. Now we have to show that the 3 altitude feet, points that came from a totally different construction, also lie on this same circle. Here is the move. Pick one altitude foot. Call the foot h sub a, where a is the side it lands on. Pick the midpoint of side BC. Call it m sub a. The altitude from vertex A is perpendicular to BC, and the altitude foot h sub a is on side BC. Thales said this: any right angle inscribed in a triangle places its vertex on a circle whose diameter is the hypotenuse. The right angle and the diameter are the same fact. Apply this to the altitude foot. The altitude foot sits at a right angle. That right angle forces it onto a circle. With a little bookkeeping using the midpoints, you can show this circle is exactly the circle through the medial triangle. 6 points down, 3 to go. The third trio is the most magical part of the proof: the midpoints between each vertex and the orthocenter. Here is the cleanest way to see it. There is a transformation called a homothety, a scaling map centered at a fixed point, with a fixed ratio. We are going to use a homothety centered at the orthocenter h, with ratio 1/2. A homothety centered at h with ratio 1/2 takes any point P, draws the segment from H to P, and outputs the midpoint of that segment. It is a simple map, shrink toward H by a factor of 2. Watch what this homothety does to the original circumscribed circle of the triangle. The circumscribed circle passes through the three vertices A, B, and C. The homothety sends each vertex to the midpoint between it and the orthocenter, 3 of the 9 points. So the homothety sends the original circumcircle to a smaller circle that passes through these 3 points. The smaller circle has half the radius of the original, and its center is the midpoint between H and the original circumcenter O. We have already shown that the medial triangle and the altitude feet sit on a circle. With a careful argument, this circle has the same center, the same radius, and contains the same 6 points as the homothety image. They are the same circle. Therefore, the third trio, the midpoints to the orthocenter, also lie on the same circle. All 9 points, one circle, half the radius of the circumscribed circle, centered at the midpoint between the orthocenter and the circumcenter. That is the proof. While we are here, we have stumbled into a second classical theorem, almost as surprising. The original triangle has 3 famous centers: the circumcenter, the center of the circumscribed circle, the centroid, the average position of the 3 vertices, and the orthocenter, the meeting point of the 3 altitudes. They are defined 3 different ways. There is no obvious reason they should be related. Euler proved in 1765 that they are collinear. They lie on one line. The circumcenter, the centroid, and the orthocenter, in that order. The line through them is called the Euler Line. And the centroid sits exactly 1/3 of the way from the circumcenter to the orthocenter. The ratio is fixed, 1:2, forever, for every triangle. The 9-point center we just constructed sits at the midpoint between the orthocenter and the circumcenter, which means the 9-point center is also on the Euler line, 4 famous centers in one straight line. Triangles, viewed casually, look like simple shapes. 3 sides, 3 vertices, end of story. But every triangle hides this, a single line on which 4 of its most important points are forced to sit, and a circle whose radius is exactly half the radius of the circumscribing one. The geometry of the triangle is layered with hidden order. We end with Feuerbach's other discovery, the one he published in the same pamphlet in 1822 when he was 22. Every triangle has an inscribed circle, the largest circle that fits inside the triangle, tangent to all 3 sides. It also has 3 excircles, circles outside the triangle, each tangent to one side and the extensions of the other 2. 4 special tangent circles, ancient, studied since Apollonius. Feuerbach proved this. The 9-point circle is internally tangent to the inscribed circle, and it is externally tangent to all 3 excircles. The 9-point circle touches all 4 of these other special circles perfectly, not approximately, exactly, for every triangle. 4 tangent points. The point where the 9-point circle touches the inscribed circle is called the Feuerbach point. It is one of the most studied special points in all of triangle geometry. Tens of thousands of named points associated with the triangle have been catalogued in the Encyclopedia of Triangle Centers. The Feuerbach point is entry X11 on that list, listed historically among the very first, considered one of the most important. Feuerbach died in obscurity in 1834, age 33. He never held an academic position. The pamphlet sold poorly during his lifetime. But the theorem he found while teaching teenagers about Euclid is by any reasonable measure one of the most beautiful things ever proved about the simplest shape in geometry. 3 sides, 3 vertices, 9 special points. One circle containing them all, tangent to 4 other special circles in 4 perfect points, hidden inside every triangle you have ever drawn.